Hey guys, it's Raj here, and today I'll be going through the concept of planes in vectors in H2 Math. So in the previous few videos, we talked about lines, and we learned that lines are a collection of points, right, that are all collinear, and they have one degree of freedom, namely that you can describe lines by writing r equals to a plus lambda b, and this lambda can be any real number, So the set of all points corresponding to all values of lambda would form the line. So why that works, right, is because we have this visualization where we have the line L that we want to describe. Then let any point on the line be described by the position vector A. Then the directional vector, we have a directional vector B that is parallel to the line. And now every point in the line can be described by one value of lambda. So in this case, this looks like kind of like lambda equal to 2, lambda equal to 1 will be somewhere over here, and so on. And by varying lambda across all real numbers, you form the entire line. So it's kind of like a walk, right? So your guy over here, the R guy, you first tell it, hey, travel to this point A on the line. Okay, so that's this A part. Then now you add it, right? And remember vector addition, we do it tip to tip, right? The tail of the thing to the head of the previous vector. Then by adding this vector on, you are letting it walk along the line. So in the end, the net position vector will be every point on the line. So that's briefly what lines is. And we'll see that planes is actually not really that different. We're just allowing another degree of freedom. So let's just write the equation for plane is actually this plus another vector c, where so lambda and mu are real numbers. So you might be wondering, what has happened, right? Um, so what happens is that c is another vector that allows us to walk in another direction on the plane. So um, imagine you have a plane here. Okay. So the way I like to illustrate this is by first drawing the line. So we are familiar with the line already, right? So we have A and then we have B like this. So let's say, so right now we have A plus lambda B, right? So with the line, and now we allow another degree of freedom. So now we allow C. So C is a vector that is not parallel to B. So important note, right, is that C cannot be parallel, not parallel to B. And what not being parallel means is that they are not scalar multiples of each other. You cannot find a scalar that scales C to be equal to B. So you can revisit my miscellaneous properties video on vectors if you're not familiar with the idea of parallel vectors. Okay, so yeah, so where do we continue? So by adding on another mu C, right, we are now allowing the guy, right, who was originally walking along the line to venture out from there. So let's say he walked along the line, let's say he walked A plus, let's say 2, let's say he walked lambda equal to 2, and let's say he's at this point. Then by adding this additional term mu C, we allow him to venture out in another line, in a line that is not parallel to this current line at all. So he can walk out, let's say to mu equals to 1, or he can walk out to mu equals to 2, and so on. And he can choose any value to walk out in the C direction. So yeah, so by in so doing, right, we start off, so in so doing, you think of it as a constructive thing. So let's say with the origin, and we want to describe a point, right? So then that would be just r equals to a. That's how you describe a position vector of a point. Then what if I want to describe a collection of position vectors, right, which are all the points on the line, then I add I add the lambda b, right? And now where b is the directional vector of the line we want to walk along. So now every value of lambda would correspond to a single point on the line. So let's say this lambda equals to 1, lambda equals to 2, and every real number we choose will give us a unique point on this line. Yeah, provided the b is not the zero vector. And then after that, now we add on the mu c. And now the mu c allows us to venture from any point on this line to any other point on the plane. So it is another dimension. So from here we can venture out. So let's say let's say this is a c vector, then this is, let's say, mu equals to 1. Then we also have, let's say, mu equals to 2, and we also have mu equals to -1, and so on. And from every point here we can go in the c direction. So, and if we let mu and lambda be any real number, then you can imagine that every single in between from all these lines will have its own line flying out. And in the end, right, that's precisely how you define a plane, right? So yeah, so if I bring over to the visual, right, let's say we have we have the in this point, in this case we have the point A. So 3 points define a plane, am I right? So we have 3 points in space, right, and they define a plane. But how does it define a plane? A plane is the plane is a unique plane that passes through all 3 points. So if, let's say, one of the points we call it A, right? So the vector OA, that's your A vector. Then now let's introduce the B vector by giving a direction parallel to the plane to travel in. But right now it's just defining a line only, right? We can only travel in a line with these 2 vectors. But if in addition to that, we provide a third C vector, right, that is not parallel to the B vector, then we can now travel along the plane by varying the values of lambda and mu. Yeah, so if let's say I move the C, if I move the C vector, if I vary the C vector, then you can see that the plane changes also. And if I can vary the B vector, then you see that the plane I'm defining also changes, right, in such a way that the 2 B and C vectors are always parallel to the plane. Yeah, so that's how you define planes using the vector equation. So I feel that the vector form, right, the vector form of the plane is the clearest way to define, is the most geometrically clear idea of how to define a plane. But there are actually other forms as well. So what we have described here so far is the vector form. So the vector form is good for geometry. The vector form is good for visualizing what happens when we define a plane. But there are other forms as well. So what other forms are there? There's the scalar product form. And there's the Cartesian form. And yeah, so what is the scalar product form? The scalar product form looks something like R, right, dot n equals to d. And yeah, so n is a normal vector to the plane. And n can calculate using b cross c. So we'll get back to that, right? But the Cartesian form will be nx x plus nyy plus nzz equals to d. And this is actually just an expansion of the dot product. So if you go from the scalar product form to the Cartesian form, we just let r equals to x, y, and z, and n, the normal vector, equals to its component. And then we just expand out the dot product to obtain this. So the Cartesian form is also understood in terms of the idea of degrees of freedom and constraints, but we'll go into that in the next video. So in the next video, we'll do this scalar product form, and in the following video, we'll do the Cartesian form.